So let's talk about this concept of mole fraction. Mole fraction is basically another way of expressing concentrations, right? And in this chapter, since we're dealing with gases, we're going to apply this concept to gases. So what do we mean by mole fraction? Well, the mole fraction of a gas is the fraction of all the molecules in a mixture that are of a given type. So in other words, the mole fraction would be the number of moles of that gas divided by the total number of moles of all the gases in the mixture, all right? So if you have several gases in a mixture and you want to find the mole fraction of one of them, you take the moles of that particular one gas and divide it by the sum total of all the gases in the mixture. Now, please note that because you're dividing a mole value here by a mole value here, that means that the mole fraction here will have no units because the mole units will cancel out, all right? Another thing I should mention is that the fact that the mole fraction here will be a fraction. In other words, it's going to be a larger number at the denominator here and a smaller number would be the numerator, which means that the mole fraction can range from a minimum of 0, which would mean nothing is present, to a maximum of 1, which would mean that there's no mixture and there's only one component, all right? So basically, you cannot have a mole fraction which would be greater than 1. It has to be some value between 0 and 1, all right? Okay, so when it comes to gases, if the pressure and volume are the same, then the mole fraction can also be calculated using the pressures of the gas in the mixture compared to the total pressure. So therefore, the mole fraction can be expressed as, in this case, mole fraction of gas 1 is equal to the partial pressure of that gas divided by the total pressure of the gaseous mixture, right? And therefore, we can rearrange it to get the pressure of a gas if we know what the mole fraction is and we know what the total pressure is. So we can use this equation to do that kind of calculation. All right, so with that out of the way, let's look at this example. So again, they're dealing with a sample of dry air. It gives you the percentages by volume of each gas that is present. And the question is asking, what is the partial pressure of each gas in a sample of air? So basically, to answer this question, we're going to use the equation P1, pressure of gas 1 is equal to the mole fraction of gas 1 times the total pressure, right? Now, in this case, they did not give us directly the mole fraction. They gave us the pressure, or I should say the percentages, right? So for example, they gave us the percentage of nitrogen here. Well, it turns out that that percentage can be expressed as the mole fraction, right? So therefore, to find the pressure of the partial pressure of nitrogen, we simply take this fraction here, which is 78.08%. We can represent it as 0.7808 and multiply that by the total pressure. What's the total pressure? Well, it's given right here, 1.000 atmospheres. 1.000 atmospheres. So the answer becomes 0.780, 8 atmospheres. All right? And basically, we do the same thing for the other gases. So for oxygen, that would be 0.2095 times 1.000 atmospheres, and that will give you 0.2095 atmospheres. And then argon, pressure of argon will be equal to 0.93%. So what that means is that when you convert it to the decimal number, it's 0.0093 times 1.000 atmospheres. So that's going to be equal to 0.0093 atmospheres. And then finally, in the case of carbon dioxide, that would be equal to 0.0004 times 1.000 atmospheres, and that would be equal to 0.0004 atmospheres. All right, and that's basically it. That's how we answer this question. All right. Okay. So let's talk about applying Dalton's law to situations where we're collecting gases over water. Now, there are certain gases that it's very convenient for us, or more convenient for us, when we're producing them, that we collect it over water. Now, the thing is that there's some shortcomings, or I should say disadvantages, with this method. And that one main disadvantage is that this method is only used for gases that are very insoluble in water. So you would not use this to collect a gas like, for example, ammonia or hydrogen chloride, because those gases are soluble in water. But gases like oxygen, hydrogen, and organic hydrocarbons like methane and so on, those gases can be collected using this method. So the diagram here shows you how this method works. Basically, you'll have the oxygen gas generated, and oxygen is the gas that is used in this example, is generated in some reaction vessel and is led into this setup right here. So this setup consists of a trough filled with water and a jar filled with water. You have this hose leading from the reaction vessel into the jar, and as the gas is produced, it goes up and is collected above the water. That gas exerts pressure, so basically it forces the water level down, and we continue to calculate, or I should say collect the gas until the water level inside the jar is the same as the water level outside. Now, the reason why we do that is that we want to ensure that we know what the pressure of the gas, what the total pressure here is, and that would be equal to the atmospheric pressure, which is acting on the surface of the water, right? So therefore, once we establish that these lines here, the surface of the water is in line with the surface of the water outside the trough, then we know that whatever the pressure inside here, that would be equal to the atmospheric pressure. Okay, now, as stated here, the gas is collected here, but it is going to be saturated with water vapor. So inside here, there are actually two gases that is present. One is oxygen and the other one is water vapor, right? So therefore, we know that the total pressure, let me write this down here because I don't see it here. Well, it's actually here, but written in a different form. So the total pressure of the gaseous mixture, whoops, sorry. The total pressure, um, whoops, okay. The total pressure of the gaseous mixture will be equal to the vapor pressure plus the pressure of the gas. In this case, it's oxygen, right? So therefore, if that is true, then this is true. The pressure of the gas, in this case oxygen, will be equal to the total pressure minus the vapor pressure of water. And since we know that the total pressure here is equal to the barometric pressure or the atmospheric pressure, then we can write this down. The pressure of the gas will be equal to the barometric pressure minus the vapor pressure of water. All right? So basically, we can calculate the pressure of the gas that is collected if we know two things. If we know the barometric pressure and if we know the water vapor pressure. Now, the barometric pressure, we can actually get that. There's an instrument known as a barometer, which is used to determine the barometric pressure. So basically, if you're doing this experiment, all you'd have to do is check out that instrument and take that reading, and that goes here. As far as the water vapor pressure is concerned, that is dependent on the temperature. And there are tables that have been produced which gives you the vapor pressure of water at various temperatures. So if you measure the temperature and then you check out the corresponding water vapor pressure, then that will be placed here in this equation. So once you know the barometric pressure and you know the water vapor pressure, then it's a simple calculation to determine the pressure of the gas that is collected over water. All right? So to illustrate this, we're going to look at this example right here. So the question says hydrogen is produced in the following reaction. In the following reaction is collected over water at 22 degrees. All right? When the barometric pressure is 742 torr. So they gave you the balance equation, and the question is asking what volume of the wet gas will be collected in the reaction of 1.50 grams aluminum with excess HCl. So what I'm going to do is I'm going to try to move this up so I have some space down here to work with. Oops. Okay. This should be enough. Okay, so basically, and there's one thing that is missing from this question, and that is the vapor pressure of water at 22 degrees. So what I'm going to do is look that up. So vapor pressure of water at 22 degrees Celsius. And according to this, the vapor pressure of water at 22 degrees Celsius is, okay, you know what? Let me do this here. 22 degrees Celsius. Okay, I'm wondering what. Okay. Let me try another source. Okay. So the vapor pressure of water is at 22 degrees is 19.8 millimeters mercury. All right. Okay. So let me go back to the PowerPoint here. And the first thing I'm going to write down here is that the vapor pressure of water, I'm going to squeeze it in right here. The vapor pressure of water at 22 degrees Celsius is equal to 19.8 millimeters mercury. All right. Okay. So what I'm going to do now is proceed with answering this question by starting off with the mass of aluminum. And based on that mass, we're going to find out how much hydrogen is produced, right? So first we have to convert to moles. So we're going to have 1 mole of aluminum above, and the molar mass of aluminum, let me look that up. So I'm going to use my molar mass calculator. So aluminum molar mass is 26.98 grams per mole. So let me go back here. So down here, I'm going to put 26.98 grams of aluminum. Go back to my black ink. And then, of course, grams of aluminum will cancel out here and here. So the next step would be the mole ratio between the aluminum and the hydrogen. So we're going to have 3 moles of hydrogen here and 2 moles of aluminum here. And we work that out. So where's my calculator? So 1.5 divided by 26.98 times 3 divided by 2. Okay, so according to my calculations, the number of moles of hydrogen is 0.0834. 0.0834 moles of hydrogen, all right? And this would be the N in the ideal gas equation. Now, what the question is asking for is the volume. Whoops, the volume. The volume would be equal to nRT over P. Now, here's the thing. We know what the number of moles of hydrogen is because we just calculated it here, right? The temperature, we know what that is because that is 22 degrees Celsius. What we do not know is the pressure of the hydrogen. Now, remember, the hydrogen is collected over water, right? So therefore, the barometric pressure would be equal to the pressure of the hydrogen minus the vapor pressure of the water. I'm sorry, not minus, plus the vapor pressure of the water. So therefore, to find the pressure of the hydrogen, that would be equal to the barometric pressure minus the vapor pressure of water. All right? The barometric pressure is 742 torr, and the vapor pressure of water is 19.8 torr because we looked it up. 19.8 millimeters mercury, which is the same thing as 19.8 torr. All right? So let's do that calculation. 742 minus 19.8, and that gives 722 torr. So down here, 722 torr. all right? So all we have to do now is to find the volume by plugging the numbers in. We know what the number of moles is, as we said before, that's 0.0834 moles times R, which is 0.0821 liters atmospheres over mole Kelvin times the temperature, which is 22 degrees plus 273, that's 295 Kelvin. So that goes here. And then we divide all of that by the pressure. Now the pressure is given in torrs, 722 torr, but we have to convert that to atmospheres. So we convert that by using this conversion factor. And basically, I'm sorry, this should be torr. And basically that's it. The torr units will cancel out here and here. The Kelvin units will cancel out here and here. The mole units will cancel out here and here. And the atmosphere units will cancel out here and here. So the final units would be in liters. So let me do that calculation. So that's going to be 0.0834 times 0.0821 times 295 divided by 722 divided by 760. So according to my calculations, and you have to round off the answer here to 3 sig figs. So according to my calculation, this works out to be equal to 2.13 liters. So that's the final answer. All right. So as you can see, this question combines a couple of things. It combines stoichiometry. That's what the first part here is all about. It combines with the ideal gas equation with Dalton's law, right? So, you know, this is one of those questions that combines a lot of concepts and principles that we were exposed to, not only in this chapter, but in previous chapters. Okay, so that's it for this example. And I'm going to stop here. And the next video, we'll be dealing with some quantitative aspects of the kinetic molecular theory. All right, until next time.